Okay, hello. So today we're looking at question 382, linked list random node. Given a singly linked list, return a random node's value from the linked list. So each node must have the same probability of getting chosen. We're supposed to implement a solution class where it initializes the object with the integer array nums, and then getRandom function will help us choose a random node from the list and return the value. Note that all the nodes again in the list should have like the same probability of getting chosen. So example 1, we can see that every time we call getRandom function, we return a randomly choose like a node's value. And yeah, I guess that's about it for the explanation. And now we look at some constraints and follow-ups. Given the number of nodes in a linked list will be in the range 1 to 10 to the power of 4, and node values ranges from negative 10 to the power of 4 to 10 to the power of 4. At most, 10 to the power of 4 calls will be made to getRandom. So we have like two more follow-up points. You can kind of think of it as like additional constraints, I suppose. What if the linked list is extremely large and its length is unknown to you? And can you solve this efficiently without using extra space? Okay, so see, if we have like without these two follow-up points, I suppose one of the ways we can do this is imagine like asking someone to pick like a random ball out of a box, right? Where we have like an extra space with all the nodes to be picked all in that space, and we can just like have a randomizer to like randomly choose a ball from the whole space. But the thing is, the follow-up suggested that we can have a solution that doesn't involve allocating extra space, and we have to think of the situations where the list is super long and we don't know the full length of it, right? So this question is like more of a I suppose like a technique question more than like a logical question, because it uses a math like thing called reservoir sampling. So I can't spell. Oh, I think I can. Okay, reservoir sampling. Why is this not okay? I guess it's like viewable, right? Okay, legible. Okay, I mean, it's kind of getting to me how it's not like in a straight line. Okay, perfect. So like I suggest watching the YouTube video, like I link below in the description box for a more detailed explanation of how reservoir sampling works, because in this situation I'm just gonna briefly explain it in the context of this question. So yep, okay, so basically instead of thinking like we have to have like all our options in a whole space and then we pick one, we can instead think of it as we pick one, and then as we go along like down the linked list, decide if we want to replace our picked node's value or not, right? So we're gonna have something called picked, and we always pick the first one, like always, right? But this is not our final picked value, because we want to go down after we pick it the value, let's call it the node for like simplicity's sake, because notes value is a mouthful. Okay, never mind, like notes value. As we go down the linked list, we decide if we want to replace this picked value or not. Okay, so probability, let's like try to work out like the probabilities of like picking each node and seeing if it makes sense or not, right? So the probability of one getting picked in the end is so this we'll call it I equals 1, I equals 2, and I equals 3. Probability of picking one, because this is the first node, is 1, I over I. And but like it doesn't end there, right? So okay, this is our current pointer. We have to traverse down the whole linked list, right? So but okay, so when our current pointer reaches this node 2, for this node not replace our picked node 1, we have to multiply the probability of this node 2 not getting picked. So the probability of that happening is 1 minus away the probability of 2 getting picked. So the probability of that happening is 2, because 2 is I plus 1, right? Okay, perfect. So okay, great. So when it reaches this node, the probability of 1 getting picked now is decreased to 0.5, because right, like we have to account for the probability where node 2 is not picked. Let's see what happens when our current pointer shifts to node 3. Probability of 1 still remaining in the picked box and not getting replaced is now 1 times half times 1 times let's see, 2/3, right? Because now we have to account for this, the probability of node 3 not getting picked, and this works out to 1 over 3. Yeah, so if we throw in like a few more examples, we'll see that probability, this value will always end up to be equals to like 1 over n, where n is the total number of nodes in the list that we're looking at. But the fun thing with this reservoir sampling method is that we don't need to like know the value of n beforehand, right? Because you can see that like once my current pointer reaches here, I already know like what node value I'm gonna end up with, right? So that's like the very rough idea of how the reservoir sampling method works. Yeah, okay, sweet. So I guess we can start like implementing this reservoir sampling. Okay, but before that, let's just like take note of what needs to be initialized. So we can see that we need our current pointer to kind of traverse down the traverse down the linked list, and then we also need to like import a randomizer to help us decide if when we reach that node, should we or should we not pick it to replace our picked node or not, right? So the randomizer, in Python we have something called random.random, and then this gives you a value between 0 to 1 in this range. I think it's inclusive, yeah. And then to decide if we want to pick node 2 or not is if the random value, like the output of this, is less than, I don't think it doesn't really matter if it's like less than or more than, wait, let me think. Oh no, it does. Okay, yeah, it should be less than. If it's less than 1 over like that node's index, so in the case of 2 it's half, in the case of 3 it will be less than minus 1/3. Then if it's true, then we replace a picked element with that current node. If it's not true, then we don't replace it, and then we move on. Okay, so let's try. We need to kind of, I keep saying kind of, we need to initialize the head in this init. And what did we say we need again? We need the picked pointer. We need the variable to hold the picked value, right? Picked equals, let's just put it to the first value, I think. Wait, we have to always return something, right? Okay, yeah, so let's just like head dot value, and then current pointer points to head, and yeah, I think we're done with the initializing, and we can start. Okay, while current, so while we're not looking at a null node, a none node, while current, we also need like a value, like a counter value, right, to help us keep track of which which index we're at, right? So I think we can start from 2, so I'll initialize it to 1, and then I'll make current dot next. It's in the range 1. Okay, so it at least has 1 node. Okay, head dot. Okay, if it's just 1 node, then we always return that node, right? Maybe we can get that out of the way first. If current not current dot if not head dot self dot head dot next, return what? Self dot head dot value, because it's just 1 node. So the rest of the examples below, it will be at least 2 nodes and more. Okay, so I'm gonna initialize current to point to head dot next. We'll start from head dot next. I think we could have started from like the head, but I don't know. I feel like this will be easier. Okay, so while current, what we want to do is, oh, I forgot to import random. If, oh, I need to add in all the selves. Current, if current, this should be 2 now, because we are starting from this second node, right? So while current if random dot random is less than 1 over I, then our picked will now be current dot val. Yeah, right. Okay, so then after that's done, we need to remember to increment our I plus equals to 1, and then current dot next. Is there anything else that we missed out? No, right? I think no. Okay. Return picked. Picked. Okay, let's see if we missed out on anything. I don't know, I feel like something feels off. Oh, okay. Let's see if it works. Oh, okay, perfect. So that's it for today's video. Thank you for watching.